Uh, so in our previous class, we started VBT. VBT explains magnetic properties of complexes, hybridations, and their structures. Already some exemptions I gave to you. What are those? With CO plus 3, please keep in mind, my dear, with CO plus 3, H2O acts as strong ligand. That's very, very important. With CO plus 2, ammonia acts as weak ligand. With Ni plus 4, weak ligands acts as strong ligands. 4D and 5D series elements. For 4D and 5D series elements, all weak ligands acts as strong ligands. These are exemptions. Please keep in your mind. Okay, now. Please keep in your mind. A number of times, a type of question is asked in your objective. That is mains and advanced levels. Let us observe some examples. What is that? CuNH3 4 times plus 2, my dear. First of all, hybridization is, what is the hybridization? Shape, magnetic property, mu is equal to under root n into n plus 2 is equal to how much? This is my question for that complex. Okay, now next. Same, NiCO4. This is the complex. NiCO4. For that one also, I want like something same. NiCN4 times. NiCN4 times. For that, what is the NiCN4 minus 1? For these complexes, what are the hybridations, shape, etc. Okay. First of all,
Sir,
you can identify.
Sir, for Ni4 plus all act as weak ligand, right?
For Ni4 plus,
Yes.
weak ligands acts as strong ligands.
Yeah, okay.
But it is here, I don't know what is the oxidation state. Tell me your side.
Okay, sir.
Arya? Are you doing? Try to explain all these points for all these three complexes.
Sir, should we say the answer?
What?
Sir, answer will tell.
I answer, I will explain. You don't worry.
Okay.
So first one, mu value root 3, sir.
First of all, tell me the hybridization.
There will be
SP3, SP3D.
SP3D. Okay. What is your answer, Anubhav?
Sir, SP3.
SP3. I will explain. Wait. Here, copper. What is the oxygen state? I don't know the situation. X plus 4 into 0 is equal to plus 2. X is equal to plus 2. Am I correct? Therefore,
Yes.
Here copper is in plus 2. Copper atomic number 29. Z value. Nothing but
Sir, yeah. Yes.
4s1 3d10 is the outermost electronic configuration. Plus 2 means losing of 2 electrons. One from S, one from D. Okay, now that is overall.
Yes, sir.
Here 4s0, 3d9 is the configuration. I'm writing 3d, 4s, 4p. 3d9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. So these are T2G orbitals, these are EG orbitals. Okay, 3 orbitals and 2 orbitals. So because this NH3 is a strong ligand, this NH3 is a strong ligand. First of all, see here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is the way to fill up the electrons. Did you understand?
Yes, sir.
First of all, you should fill T2G and then you can enter it into the EG level because T2G orbitals having lower energy than EG orbitals. So today we will discuss why like that CFT. Okay. Now,
Okay, sir.
this NH3 is a strong ligand or weak ligand? Strong ligand. So
Strong,
here 3D orbitals have one empty electron, one unpaired electron. Because of strong ligands, because of strong strength of that ligand is very strong. So this unpaired electron jumping from here B orbital to this P orbital. Therefore, this is vacant. These 4 vacant orbitals are involved in because it is coordinate number 4. DsP2 is the hybridization. Okay, now how many unpaired
Yes, sir.
electrons are there? One unpaired electron. Therefore, n is equal to 1. N is equal to 1 means, so under root n into n plus 1, root 3 is the answer for first complex. Clear? That is the special case, that electron jumping from 3d orbital to 4p. So that vacant orbital is created by this NH3 ligand because it is strong ligand. So strong ligands, inner orbital complexes, 3d orbitals should be involved. If this box is completely filled with the 2 electrons, this is actually not happening. But it has only one unpaired electron. That is why that unpaired electron jumping from 3d orbital to 4p orbital. Okay, this box is
Okay,
filled
sir.
with 2 electrons. This is not happening. Then hybridization is sp2. But it has only one unpaired electron. That is why it is dsp2. Clear?
Okay, sir.
Arya.
Sir.
Arya.
Yes.
Clear?
Clear.
Okay, next. Please copy, my dear. These are all important complexes. Now, NiCO4. Here, carbon monoxide, strong ligand or weak ligand? Carbon is the donor atom. Therefore, it should be the strong ligand.
Yes, sir.
Here, nickel, oxygen state, X plus 4 into 0 is equal to 0. No charge is above on that complex. That's why it is 0. Therefore, X is equal to 0 and nickel oxygen state in this case is 0. In carbonyl complexes, oxygen state of nickel is 0. In carbonyl complexes, oxygen state of nickel is 0. Okay, now next.
Okay, sir.
Next. Now, nickel. Atomic number Z is equal to 28. 28 means S2D8 medium. It is 4s2 3d8. So now 3d 4s 4p. These are T2Z easy. This is strong. First fill T2Z. D8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. 4s2. 4s2. This is the ground state electronic configuration of this nickel in this particular complex. So do you have any doubt up to now?
No, sir.
Now, is carbon monoxide strong ligand or weak ligand?
Strong.
So because of presence of the strong ligand, these two electrons present in s orbital entered into the 3d orbitals. Now this s orbital is vacant. Okay. So because now it is a spin paired complex or spin free complex? Spin paired complex or spin free complex?
Paired.
Spin paired means
Spin paired.
unpaired electrons gets paired. It is spin paired complex. It is sp3 hybridization. Am I correct? Because coordinate number 4, sp3 hybridization. Empty orbitals are involved in the hybridization. sp3 hybridization. Is there any unpaired electron here?
No, sir.
No. Therefore, number of unpaired electrons n is equal to 0, mu also equal to 0. It is diamagnetic in case. So NiCO4 is sp3 hybridized. Because it is sp3 hybridized, it is a tetrahedral shape. If it is D2sp2, just like in previous case, that is a square planar complex. Okay, so NiCO3 4 times
Yes, sir.
plus 2 is square planar complex, but NiCO4 is tetrahedral complex. It is tetrahedral complex. Clear?
Yes, sir.
NiCO4 is a tetrahedral complex. Now, our complex is NiCN 4 times. NiCN 4 times minus 2. First of all, find out the oxidation state. X plus 4 into
Two.
cyanide has minus 1 is equal to minus 2. Therefore, X is equal to plus 2. Therefore, oxidation state of nickel is plus 2 minus. So, nickel atomic number Z is equal to 28. 28 means S2DH, 4S2, 3DH, but it is in plus 2. Loss of 2 electrons. First of all, you can remove electrons from 4s orbital. Now, after losing these 2 electrons, the electronic configuration is 4s0, 3d8. Is there any doubt up to now?
No, sir.
Now, 3d8. It is 3d. 1, 2, 3, 4, 5. 4s, 4 period. 3d8 is cyanide strong ligand or weak ligand? No doubt it should be strong ligand. So once again, T2Z and EZ condition. T2Z, EZ, strong ligand. 1, 2, 3, 4, 5, 6, 7, 8. DH. Clear? Cyanide, strong ligand. Because cyanide is strong ligand, this unpaired electron is jumping from here to here. Now it becomes paired electron. Is there an unpaired electron here? N is equal to 0. Therefore, it is
No,
a
sir.
diamagnetic. Mu is equal to 0. Now it is a DsP2 hybridized. Clear?
Yes, sir.
DsP2 hybridized. That is why it is a square planar complex or tetrahedral complex. Is this square planar or tetrahedral?
Square planar.
Square planar. All is due to because of presence of that unpaired, that is a strong ligands like that. Right? Is there any doubt?
No, sir.
No. Now tell me, my dear. PdCl4 minus 2. Here hybridization sp3 or dsp2. Because coordinate number 4 means these two are only possible. Here
Sir,
chlorine.
at
Access,
SP3.
here chlorine involved in, is this chlorine strong ligand or weak ligand? Tell me.
Sir, weak.
Weak. Here chlorine strong ligand or weak ligand? Arya. Shiva is there?
Sir,
Yes, tell me. Is chlorine strong ligand or weak ligand?
strong ligand, sir.
Weak ligand.
Why it is strong ligand?
Weak ligand.
Weak ligand. Shiva, why you are strong?
Sir, exception.
Exception. See, my dear, Shiva is correct. Palladium. Is palladium 3D electron, 3D element?
Sir,
Sir,
Is this palladium 3D element? It is not 3D, my dear.
not 3 days.
Because it is not 3D, it is either 4D or 5D, whatever it may be. For 4D and 5D metals, all ligands, all weak ligands are strong ligand. Actually, it is weak ligand, but it behaves like strong ligand here. Okay, na?
Yes, sir.
So because of high nuclear charge, with palladium, chlorine acts as strong ligand, not weak ligand. Do you have any doubt on Anubhav?
no, sir, no doubt. I wrote it wrong in my copy.
Yes. Now it is strong ligand. Whenever strong ligand is there, it is DsP2 hybridized, it is not sp3 hybridized. It is with weak ligand, it is with strong ligand, my dear. Now our chlorine is acts as strong ligand, therefore the hybridization is DsP2. Clear? Because it is DsP2, it is square planar condition. If it is sp3, that is a tetrahedral. Now what is the shape of this complex? Square planar or tetrahedral?
Square planar.
Square planar. Next. Now my question is CdCl4 plus 2. Sorry, minus 2. What is the hybridization of this complex?
That will be sp3.
Hybridization.
Hybridization. Their chlorine acts as strong ligand or weak ligand.
SP3 also, sir.
Strong ligand, but sp3.
DSP2, sir.
Huh?
DSP2, sir.
DsP2. What about Arya? Your voice is not there.
DSP2, sir.
DsP2. So actually zinc, cadmium, mercury, we know. Okay, na?
Yes, sir. D10 elements. So I think
It is
sp3.
3D, it is 4D, it is 5D. No doubt, this chlorine acts as strong ligand instead of weak ligand with cadmium. Correct or wrong?
Correct. Sir.
Because cadmium 4D elements, but not 3D element. That is why for 4D, 5D series elements, weak ligands are all acts as strong ligands. Next, cadmium configuration. That is S2D10, just like zinc. Correct or wrong?
Yes, sir. Correct.
Now here cadmium is in +2 oxidation stage. Find out. Now S2 electrons are lost. It is a D10 configuration. D10 means like this. 3D, 4S, 4PN. It is not 3D, it is 4D, 4S, 5S, 5PN. Okay. Here, 4D, my dear. 4D. Because it acts as strong ligand, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All orbitals are completely filled up. Even though it is strong ligand, no electron jumping from here to here. Because it has no unpaired electron. Am I correct or wrong?
Yes, sir.
Okay. No jumping takes place. Only these orbitals are involved in hybridization. That is why sp3 hybridization. That is why sp3 hybridization. Therefore, the shape is tetrahedral or square planar?
Tetrahedral.
Tetrahedral. CD. Even though CD is a 4D element, okay, we are expecting DsP2 because chlorine acts as strong ligand, but the actual shape is, the actual hybridization is sp3 and the shape is tetrahedral, not square planar. Shiva, clearer?
Yes, sir. Clear, sir.
If at least this unpaired electron exists, now it is jumping from here to here. Then DsP2 is expected, but here no unpaired electron. Correct or wrong? This is actually happening in zinc case, copper case. Okay, na? But no unpaired electron is there. No electron is jumping from 3D to that is 4D to either 4P or 4D. So not possible there because those electrons are fully paired up. Now is this paramagnetic element paramagnetic complex or diamagnetic complex?
Diamagnetic.
Diamagnetic, it has no unpaired electrons. These are all some exemptions. I think you learned well. Am I correct?
Yes, sir.
Okay. Anubhav?
Yes, sir.
Anubhav. So actually you know these concepts. Now these are
Sir, here fluorine is weak or strong, sir?
just a minute. Just Shiva, please wait.
Yes, sir.
Anubhav.
Yes, sir. Yes, sir.
Already you know VBD.
Yes, sir.
So are these new for you or not?
So, sir, these exceptions part, I needed to know the 45D. I didn't know the
Yes,
45D.
that is why you should learn.
Yes, sir.
Okay. Everything there should be at least one new topic, at least new point will
Yes,
appear.
absolutely, sir. That's why I don't skip the classes. Try to
So
not.
don't skip the classes.
Yes, sir.
So that is I am expecting from you. Okay.
Yes. Sir, if required, I
Yes.
will tell you and then watch the recording.
Okay, just a minute.
Yes.
Shiva,
Sir,
Shiva,
sir.
tell me.
Yes, sir.
Do you have any doubts?
ఏమైనా డౌట్స్ ఏం లేదు
ఓకే ఏదో మాట్లాడుతున్నావు కదా.
నేనా సార్ నేనే మాట్లాడాను సార్
నువ్వు కదా అయితే ఆర్య
ఇందాక చూపిన ఎగ్జాంపుల్ క్లోరిన్ స్ట్రాంగ్ ఆర్ వీక్ లేదని సార్?
స్ట్రాంగ్ నో డౌట్ బట్ స్ట్రాంగ్ అయినా కూడా అక్కడ అన్పేడ్ ఎలక్ట్రాన్ లేదు కాబట్టి ఇక్కడ నుండి అక్కడ జంప్ అవడానికి లేదు కాబట్టి చచ్చినట్టు అది sp3 అయింది. అదే నీకు డీలో అన్పేడ్ ఎలక్ట్రాన్ ఉండి ఉంటే అటు వెళ్ళిపోయేది. ఓకేనా?
అంటే బిట్ సాల్వ్ చేసేటప్పుడు క్లోరిన్ వీక్ లేదని అనుకుని చేశాను సార్. అంటే మిస్టేక్ ఏమైనా డౌట్?
లేదు స్ట్రాంగ్ లేకండే బట్ sp3. ఓకే. Now, my dear, the most important topic in complex compounds, that is CFT, crystal field theory. So, Anubhav, this is your topic.
Yes, sir. I mean,
See-
this is the topic I have the most doubt in.
Ah,
Else is like I need to know, but more confident than CFT.
okay. CFT, crystal field theory. What is this crystal field theory? See, my dear, our ligands, strong, weak, already we used that word. Why some ligands are strong, why some ligands are weak, that is clearly explained on the basis of this CFT. Based on that, they gave a series of strength of ligands, that is nothing but spectrochemical series. Already we used that. Why that series appeared, why the series is coming out, that is here we are going to discuss it. Why some ligands are strong, why some ligands are weak. Okay. See, my dear, it is completely based on splitting of d orbitals in metal ion. Because d orbitals are present in metal, those d orbitals here are going to split because of presence of ligands. The splitting is either strong or weak, that is depending on the strength of the ligand. Why those d orbitals are going to be split? That is explained on the basis of this CFT. And you see here, actually, my dear, here we are discussing about the d orbitals first of all. D orbital shape set. How many d orbitals are actually available for us? 5 d orbitals are available. What are all those 5 d orbitals? Those are dxy, dyz, dxz, dx square y square, dz square, my dear. These are the 5 d orbitals. dxy, nothing but it is x-axis, y-axis. These are the sorry. X-axis, y-axis. In between these two axes, our electron density is available. This is dxy, my dear. Similarly, dyz. Between the axis, electron density is there. This is dyz. Next, dxz. Between the eyebrows, electron density is there. It is a dxz. Next, dx square y square. It is x-axis. It is y-axis. On the axis, electron density is there. It is dx square y square. dz square, my dear. This is z-axis. It is x-axis. So electron density on the axis, there is a tie. It is dz square. These are the shapes of the d eyebrows. All you know very well. Okay, ra? So dxy,
Yes, sir.
dyz, dxz. Their electron density on the axis or between the axis? Tell me. These lobes
So
are
between the
electron
axis.
density. So that is one electron density between the axis. But squares, x square, y square, and z square. So if the square is there, those are plus electron density on the axis. Correct?
Yes, sir.
Now, actually, all these 5D orbitals have same energy, and that is why these are considered as degenerate orbitals. All these 5 orbitals are having same energy, so these are called as the degenerate orbitals. So, but because of variation in the availability of electron density along the axis and between the axis, these are splits into, sometimes it is possible, these 3 orbitals having same energy, and these 2 orbitals having same energy. So these 3 orbitals are, we call it as T2Z orbitals, triply degenerate orbitals. These 2 orbitals are considered as easy orbitals, that is again, no use any, that is a doubly degenerate orbitals. So T2Z orbitals are easy orbitals. Do you have any doubts? Because of variation in the electron density between and along the axis. So between the axis, 3 orbitals are T2Z orbitals, triply degenerate. These are easy orbitals. Actually, all these are same energy. All these 5 orbitals have same energy. All these 5 are degenerated. But in the presence of ligand, in the absence, these are equal. But in the presence of ligand, so these are like this: triply degenerate and doubly degenerate. Clear? In the presence
Yes,
of ligands, these are not, all these 5 are not degenerate. But in the absence of ligands, these are degenerate. Do you have any doubt up to now?
yes, sir. There are no doubts.
So, in the presence of ligands, either strong or weak, whatever it is, 5D orbitals
Sir,
not degenerate. It break down into 3 plus 2. These 3 orbitals are triply T2Z orbitals. These 2 orbitals are easy orbitals in the presence of ligands. But in the absence of ligands, all 5D orbitals, tell me, are degenerate.
degenerate.
Don't split any. Don't split that. Okay.
Sir.
So it is only presence of ligand and absence of ligand. But in our complexes, everywhere there should be a ligand, either strong ligand or very weak ligand. Am I correct? In complexes, there should be ligands. Therefore, there should be splitting there. That means all these 5 orbitals break down into 2 sets. One set having 3 orbitals, one set having 2 orbitals. 3 orbital set is called as a T2Z orbital. 2 orbital set is called as easy orbital. Okay. Now,
Yes, sir. Sir, I have one
let us
doubt.
discuss. Yes, tell me.
Sir, it's not a doubt, but a question. So the reason for this splitting you said was due to different availability of electrons.
No,
Then
presence and absence of electron. Presence and absence of d orbitals. That is
sir,
actually what happened. See. Let us assume actually what happened here. Actually, I'm going to skip this point. So you ask, that's why I'm explaining. See here. See, my dear, we have 3 axes. Cartesian axis, x-axis, y-axis, and z-axis. So it is the origin of these three axes. Let us take a metal is placed at the origin. Our complex metal. Okay, now. Okay. Now
Yes, sir.
it is x-axis, y-axis, and z-axis. It is positive, it is negative, positive, negative, positive, x-axis, negative, x-axis. All we know very well. Now let us take coordination number 6. Next, my dear. Coordination number 6. That means all I am taking monodentate ligands. I am taking monodentate ligands. Now total number of ligands is equal to 6. Am I correct? Because monodentate,
Yes, sir.
coordination number 6. So total number of ligands are 6. All those ligands just place along the x-axis, y-axis, on the axis, my dear. These are all ligands. All these ligands where we place it? On the axis or between the axis?
Sir, on the axis. Okay,
All
sir.
these 6
Understood.
ligands on the axis. Where that metal is there? Just at the origin, correct? This metal has a d orbitals. Am I correct? Those d orbitals, some of the d orbitals, the electron density on the axis, and some orbitals have between the axis electron density. That is we know well. Now, so these 6 ligands from the metal, let us assume at infinite distance. That means there is no attraction, there is no repulsion between this metal and ligand. Okay, now this is for our assumption.
Yes, sir.
First of all, I am taking these ligands between on the axis, very far away from the metal. There is no attraction repulsion between the metal and ligands. Okay. Now, these ligands trying to approach metal end because to form complex. Complex is formed because of ligands approaching that. So there should be a bond formation between metal and ligand. Then only complex is existent. That means these ligands approaching towards metal. So that means the distance between metal and ligand increase or decrease when ligand approaching metal?
Decreases.
Decreases. That means it is on the axis or between the axis it is going to approach towards metal?
On the axis.
On the axis. See, my dear, actually, when it is approaching nearer to each other, how many d orbitals are there? 5 d orbitals are there. Actually, all these 5 d orbitals, because ligand is nothing but lone paired species, it can donate its electron pair to the metal. Now, d orbitals also having electron pairs, also having electrons. With these electrons and these electron pairs, there should be some repulsion exists. Am I correct or wrong?
Yes, sir.
Electrons present in the d orbital of metal and lone pair of ligand, those, no doubt, those two are negatively charged, there should be a repulsion. At the beginning, these repulsions experience, that means all these 5 orbitals electrons equally experienced the repulsion with these ligands. That's why, see here, that is why actually these are the 5 d orbitals, my dear. Okay, so all these are degenerate, but that is when it is possible if ligands are very far away from each other. Ligands
Yes, sir.
and metal are very far away, no attraction, no repulsion are there. All these 5 d orbitals are degenerate. Now ligands approaching metal, all the 5 d orbitals electrons equally experience a repulsion. Because of repulsions, all these orbitals have equal repulsions and their energy is increased. So that means all these 5 orbitals equally increases their energy. Clear? So in this direction, energy is increased. Why this is happening? It is ground stage. It is excited state, my dear. So this is if ligand is at infinite distance, low energy. If it is ligand approaches approaches towards metal end, but equally experience the repulsion. Am I correct or wrong? Up to now, do you have any doubts?
Yes, sir. No doubt, sir.
Now this ligand approaching very nearer to the metal. Let us assume these are not nearer to. That means in this case, the electron density on the axis, because d arbus having some of the arbus electron density on the axis, some arbus having between the axis. So now ligands are approaching towards metal on the axis. That means some of the orbitals having electron density on the axis experience more repulsions because approaching is on the axis, already electron density also on the axis. So see, let us assume it is between the axis orbitals, my dear. It is on the axis orbital, my dear. Okay, now ligand approaching towards on the axis orbital. That means this electrons present on the axis experience more repulsion when compared to between the axis. Am I correct or wrong? Because the distance between
Yes, sir.
this orbital and this orbital is more than that of these two orbitals, these two electrons. Correct or wrong?
Correct, sir.
That means this orbital experience more repulsion than that of this orbital. Correct?
Yes, sir. Yes, sir. That is.
Now this orbital is nothing but the orbital where electron density on the axis, nothing but
Yes, sir.
dx square y square
Dx
or
square.
dz square. Okay,
Yes, sir.
this is between the axis, nothing but dxy, dyz or dxz. Correct?
Yes, sir.
That means these orbitals experience less repulsion than that of these orbitals. Correct or wrong?
Correct, sir.
These three orbitals experience less repulsion than that of these two orbitals when ligands approaching towards metal on the axis. Correct or wrong?
Sir, that
Tell me.
sir, the three orbitals, T2G orbitals, sir, you have given dxy, dyz, and dxz. They
Yes,
experience
dxy,
less.
dyz,
You are asking that they experience less repulsion.
less repulsion
Yes,
when
sir.
compared to
Yes,
these
sir.
orbitals.
Yes, sir. That is true.
Correct? So
Yes, sir.
because of that, there is a repulsion variation between
Okay.
dx square y square dy square and dxy yz xz. Because of that, these 5D orbitals break down into 3 and 2 sets. 3 orbitals having low energy, 2 orbitals having high energy.
Okay.
Okay, because these orbitals experience more repulsions, more energy is there. That's why their energy, these two are nothing but dx square y square, dz square. These three are dxy, dyz, dxz. Okay, because of that repulsion variation,
Yes, sir.
okay, those 5D orbitals are splits into 3 and 2 sets. 3 set orbitals are nothing but T2Z orbitals, 2 sets orbitals are nothing but EZ orbitals. These are XY, YZ, XZ orbitals. These are X square, Y square, and Z square orbitals. So it is due to variation in the repulsion between electron pairs on ligand and electrons present in the d orbitals of metals. This splitting is totally due to that repulsion. If this ligand is strong, it is approaching to a metal towards very strongly, very high speed. Because of that, more repulsion occurs. Because of that, that ligand, if splitting is more, that ligand is strong. If splitting is less, that means repulsion is less. That's why that ligand is taken as weak ligand. Okay, now
Okay, sir.
that strength of the ligand clearly explained on the basis of splitting. This is nothing but crystal field splitting. That is nothing but crystal field splitting. That is why at the beginning 5D orbitals are degenerate. After some time, a little bit, all those 5D orbitals are degenerate, but having something more energy than that of initial case. But even ligands approaching towards metal, automatically they are break down into 2, 3, and 2 sets. That splitting is nothing but crystal field splitting. That is the basic for this 3FTL. Having any doubts?
No, sir. Just writing the.
Is this clear above for you?
Yes, sir.
Why that is
Very
breakdown into 2 and 3?
Yes, sir.
Okay.
Totally, sir. Yes, sir.
Okay, now Shiva, clear?
Yes, sir,
Why
clear.
there?
Yes, sir, yes, sir, yes, sir.
Yes, yes. Finally, my dear, I'm present once again rewriting that diagram. These are T2G orbitals. These are EG orbitals. EG orbitals are nothing but dx square y square dz square. EG orbitals are nothing but dxy dyz dxh. Okay, na? T2G EG orbitals. Now, my dear, if it is this splitting, we call it as octahedral splitting, because we are taking 6 ligands. Coordination number 6. Coordination number 6, either it is D2sp3 or sp3d2, whatever it may be. The hybridization is the shape of the complex is octahedral. That's why it is octahedral splitting. Delta naught. If this
Okay.
splitting is more, strength of the ligand is more. Splitting is less, strength of the ligand is less. But there should be some splitting. Okay, that is delta naught, my dear. Now, so when compared to these orbitals, these 3 orbitals having less energy. Am I correct? These 3 orbitals having
Yes, sir.
less energy than that of these 5 orbitals. These 2 orbitals having more energy than these 5 orbitals. So here, my dear, because here energy is decreased, the decreasing is indicated with minus 0.4 into delta naught is the value. Okay, now next here energy, that is splitting, is increased. Because of that, it is plus 0.6 delta naught, my dear. If every electron entered into T2G orbitals, the energy of that orbital decreased by a fraction of 0.4. If electron entered into the EG orbital, the energy of that orbital, that element, increased by a value of 0.6. Okay. Now,
Yes, sir.
crystal field stabilization energy. See, my dear, for example, 1, 2, 3, 4, 5, 6, 7, total 7 electrons are there. Here also 7 electrons are there. Now, in this case, we are writing first lower orbital field and then higher orbital field. Because of that, 1, 2, 3, 4, 5, 6, 7. After filling these 3 T2, then only the electron entered into the EG. Because T2 has lower and EG has having higher, there is a gap between T2 and EG.
Yes, sir.
It is simply both the phase of strong ligand. If it is weak ligand, the difference between these two is very less. That's why, see here, it is in case of strong ligand. For example, if it is weak ligand, 1, 2, 3, 4, 5, 6, 7, like this. Because the difference is very less, that is general electron configuration taking place.
Okay.
Clear? Why
sir.
sometimes using configuration this type and that type, that is totally depending on the strength. If difference
Yes,
is
sir.
high, first T2G filled and EG is next time. If difference is low, T2G and EG filled with 1 electron and then pairing takes place. It is completely depending on strength of the ligand. Strong ligands are there, first T2G filled and then EG. If weak ligands are there, T2G filled with 1 electron and EG filled with 1 electron each, and then pairing takes place. It is in case of weak ligand. Because of that only, previously I wrote all these 5 orbitals into T2G set and EG set. Nothing but these are these orbitals, these are these orbitals set. So totally we are correcting, we are discussing both are at one place. I don't want to write that splitting. Okay.
Yes, sir.
Clear? Okay,
Yes.
now my dear, if it is strong ligand, what is crystal field splitting energy, stabilization energy? Crystal field stabilization energy is nothing but crystal field stabilization energy is equal to number of T2G electrons into 0.4 minus 0.4 plus number of EG electrons into plus 0.6 overall delta naught L. In this case, my dear, how many number of T2G electrons? 6 electrons. 6 into minus 0.4 plus number of EG electrons 1, my dear. Okay, 1 into 0.6. So overall value into delta naught, that is minus 2.4 plus 0.6 delta naught. How much is the value, my dear? Minus 0.4, that is 1.8 minus 1.8 delta naught. Delta naught value is given to you sometimes in your exam. Use that value, multiply that, after that you will crystal field stabilization. Okay, na?
Sir,
Yes.
sir, there is one. Sir, there is a part of pairing energy.
Pairing energy. Yes. I will explain.
It will be
Wait.
subtracted from. Okay.
I will explain. Wait.
Okay. Sir.
Next. So up to this, is there any doubts?
No, sir, no doubt.
So that means in case of strong ligand, this is the electron configuration of D7N. D7 configuration.
Sir, one doubt.
If weak ligand is there, if weak
yes,
ligand
yes.
is there, if weak ligand is 1, 2, 3, 4, 5, 6, 7, then crystal field stabilization energy in case of weak ligand for D7 configuration is equal to how many electrons? 5 into 0.4 minus plus 2 into plus 0.6 overall delta naught. Okay. So 5 fours 22.0 minus plus 12 1.2 delta naught. Here it is minus 0.8 delta naught minus. It is in case of weak ligand. It is in case of strong ligand for D7 configuration. Do you have any doubts?
No, sir, no doubt.
Okay, delta naught value is given to you, my dear. If delta naught value is not given to you, that delta naught is nothing but energy, and E is equal to hc by lambda. That wavelength is given to you. Okay, so calculate E value, nothing but delta naught. Use that delta naught there. Clear? N is the number of photons. Sometimes N is applied, N is the number of photons. This is the formula used to calculate this delta naught. Okay, now wavelength is given to you. Or frequency is given to you, or C by lambda is equal to frequency, my dear. That is delta naught is equal to E equal to NH nu. N is number of photons. Number of photons having frequency nu. 3H4. Number of photons. Okay, now. See, my dear.
Yes, sir.
So, Anubhav, you asked me about pairing energy.
Sir, another thing
That
I
means-
asked, sir,
Yes.
sir, which doubt is actually cleared, sir. I was going to ask, sir, sometimes in questions we see the delta naught's value is given as centimeter inverse, like the inverse of wavelength.
Yes,
I did not know
centimeter,
this reason. That's because,
centimeter inverse is the unit of frequency, my dear.
sir, it is wave number.
Nu, centimeter inverse is nothing but cycles per second frequency.
Yes, sir.
He is directly proportional to nu. See here,
Yes, sir.
nu.
Yes,
That's
sir.
right. So you can use nu value also, but you should calculate that E value. If he asked the same units, you can use nu.
Yes, sir.
If in terms of joules or something is there, you can calculate that nu value converted into energy.
Yes, sir. Yes, sir.
Okay, clearer.
Yes, sir.
Now,
So, say electron
Pairing
volt
energy.
is, sir, if electron volt is asked, then I can just use that one.
Yes, electron volt also one of the energy used term, energy, one of the units of energy.
Okay,
Electron
so
volts.
conversion. Okay.
Yes, conversion. Joules, electron volts,
Okay.
farads. Okay. See here. Actually, D7 configuration is this one. Only. How many pair of electrons there? Already 2 electron pairs of pair. Clear? It is actual number of pairs of electrons. But in the pairs of strong ligand, 3 pairs are there. Correct or not? In
Yes.
pairs of strong ligand, 3 pairs. How many are in excess?
Sir, one pair.
Only one pair. That is only due to strong ligand, strength of the ligand. Am I correct?
Yes, sir.
How many extra pairs of electrons are there due to strong ligand? Extra.
One, sir.
One. That is why in this case delta naught plus one pairing energy is used. That pairing energy is given. That is total crystal field stabilization energy. That means if pairing energy is given to you, crystal field stabilization energy is nothing but delta naught plus pairing energy. Pairing energy means number of extra pairs are there because of presence of the strong ligand. So that is number of extra pairs into
Okay.
itself. For that pairing, how much energy is there? That pairing energy is given to you. Okay, na?
Yes, sir.
So these are the some words. My dear, if tetrahedral complexes are there, now I am writing this is for octahedral. Octahedral. 3 orbitals, 2 orbitals. Tetrahedral is there. This is 2, this is 3. Just inverted. Because in tetrahedral case, electron ligands are approaching between the axis, not along the axis.
Yes, sir.
Okay, between the axis, orbitals experience more repulsion than that of along the axis. That is why these orbitals experience more repulsion than this one. That is why these orbitals at the down position, these are at the top position. So that means in case of tetrahedral, this is the case. It is a tetrahedral case barrier. This is octahedral case. This splitting is nothing but a delta TL crystal field. This splitting is nothing but delta naught. Do you have the ratio between delta T and delta naught? Where more splitting is there, more ligands, more splitting end.
Yes, sir.
More ligands, more splitting end. Now delta T is equal to 4/9 delta naught. This is the relation between delta T and delta naught. Clear? If delta naught is
Yes,
given
sir.
to you,
Yes, sir.
the delta T is asking it. He asks delta T by giving delta naught. By giving delta naught. Clear?
Got it. Yes, sir.
So why some ligands are weak, why some ligands are strong? Do you have any doubt? If the splitting is
No
more,
doubt, sir.
ligand is strong. If splitting is less, ligand is weak. That's why the series is obtained. That series we used, that is the spectrochemical series, my dear. Okay, this is all about CFT. So you can read well today. Today you can read well. Very, very important. So tomorrow I will take carbonyl complexes. Okay, nothing but organometallic complexes. So that is the end of our complex compound for today, tomorrow.
Sir,
Okay. Yes.
then in splitting on this